there's an echo.
Is it
Is it
mine?
mine?
I think
Yeah, I
it's
think.
me.
Yeah.
Let me see something. Hello?
Yeah, looks better now.
Ah, yeah, I was opening two things. Okay, perfect.
All right. Hey, all. So we were having technical difficulties and now we are live. I'm pleased to introduce our next speaker, Ranwa Al Mallah, who's an assistant professor in the Department of Electrical and Computer Engineering at Royal Military College of Canada. She works in the fields of artificial intelligence, network engineering, and cybersecurity. She's been focusing on federated learning, reinforcement learning, split learning for automotive security, and AI versus AI. I mean, I'm looking forward to this talk, and we'll definitely, I mean, we'll have a Q&A as well. So post your questions in the Q&A tab, and yeah, I'll pass the floor over to Ranva. Over to you, Ranva.
Thank you. I'll start sharing my screen. Let me know if all is good.
We can see it. Thanks, Ranva.
All good? Okay. Mm. Okay. So hello and thank you for the invitation. My name is Ranwa and I'm talking to you from Montreal, Canada. And the talk that I will give today is about this AI versus AI arms race on critical infrastructure. So before I start, this is a little bit of my personal background. So who am I? I'm currently an assistant professor at the Royal Military College of Canada. I'm in the Department of Electrical and Computer Engineering, and I'm part of the Computer Security Lab. I earned my PhD in computer science from the Department of Computer and Software Engineering at Polytechnique Montreal. But before that, I worked in the industry for a period of 7 years. I started as a programmer, then became a project manager in a consulting firm for various computer telecommunication network projects. After I completed my PhD, I joined the Information System Security Laboratory at Polytechnique Montreal, and I was a research assistant there. And this is where I started my research activities in cybersecurity. So I also did a postdoc at Ryerson University, now the Toronto Metropolitan University, and this is where my research was more focused on cybersecurity in transportation networks. I was in the Laboratory of Innovations in Transportation under the supervision of Dr. Bilal Farouk. He's a Canada researcher in disruptive transportation technologies and services. And so, as I said, I'm a professor, and so this talk is focused on the latest interesting research directions in automotive cybersecurity. Precisely, I see automotive cybersecurity and its supporting infrastructure as being a cyber physical system. Cyber physical systems are those systems that combine computer technology and communication technology with devices that interact with the physical world. And so, as an independent researcher, I explore security challenges in emerging cyber physical systems. The problem is that as cyber physical systems they become more widespread, malicious actors they aim at altering their behavior. And so I explore security challenges in this domain, and I do so with my team of masters and master students and PhD students in collaboration with several national university. So I will start the talk by presenting my past research in this domain, which is focused on just the design of the solutions, and I will then present to you my ongoing research, which focus on the security in the design of the solutions. And this is where I use artificial intelligence to both attack the cyber physical system and defend the cyber physical system that we're studying. And finally, I'll introduce this AI versus AI arms race, this concept that we're attempting to model and to understand, because we believe that the cyber physical systems running our critical on our critical infrastructures and on which countless Canadian businesses depend, they are vulnerable to attacks by cyber criminals. So we want to develop novel approaches to counter this threat. And imagine if it is against an AI capable attacker, then we must research. We need a research program that has the capacity to explore what happens when an AI is attacking and an AI is defending. So we need a research program that leads to a theory about this AI co-evolution that will allow us to prevent conditions of instability and conflict on our critical infrastructures. So I will start by presenting my past research on cyber physical systems, which focused on the design of the solutions. And the reason why I'm presenting this past research of ours is because I believe that most cyber physical system security research focus on solutions addressing hardware and network security. Now, those domain agnostic solutions are definitely part of the solution, but they are too generic to be able to understand and detect the sophisticated and targeted attacks that we are facing today against um, specific cyber physical systems such as the automotive network. So we are facing attacks that are so specific to the control discipline and algorithms being used in a given system. And so defenses against those attacks would have to be at least application domain specific at best, if not specific to each cyber physical system, as I call it. Meaning that in order to address cybersecurity challenge, you must have a precise knowledge of the controlled system, the control discipline, and the IT infrastructure used to implement it. And so, this past research of ours shows that before doing research on cybersecurity, we were focusing on understanding the cyber physical system. We were developing highly intelligent solutions, meaning using top down AI techniques for the planning, the design, and the operation of computer networks running on critical infrastructures. We have published those solutions in very important journals. We were focusing on networking and mobility, particularly in vehicular networks and intelligent transportation systems. So we have a deep understanding of the system. And it's only then that we can try to address the cybersecurity challenges in this domain. Um, so here are three phases. So here in three phases, actually, I will present the summary of the contributions and how we applied machine learning methods to several traffic management problems using data from the network of connected vehicles. We addressed several research questions. So in phase one, for example, um, the question was, and it's an interesting idea. The question was, can we estimate the cause of the traffic congestion that is happening at the current moment using only traffic flow theory and information exchange between the network of vehicles? I'm not talking about predicting when would traffic congestion happen, but just estimate the cause of the congestion with simply information exchanged between those CA connected and autonomous vehicles. So in other words, like can a vehicle guess if it's stuck in traffic because of an accident, because of an inclement weather, because there is a special event happening in the region, or simply because it's the rush hour and it's like recurrent congestion happening? So this is one question that we were able to address. And another question that we addressed is how and what microscopic and macroscopic traffic variables um, would we need to collect in real time everywhere on the urban road network in order to do that? So we were able to demonstrate that not only monitoring of traffic variables can be done using vehicular networks, but we were also able to extract features and train models, machine learning models, to infer on the cause of congestion that is happening. And we did so by formulating a classification problem in ML, and we generated a synthetic data set. We tested several machine ML algorithms, and these contributions led to this publication that I state here in IEEE Transactions on Intelligent Transportation Systems, which is a top tier transportation journal with a very high impact factor. And then here in phase two, for example, the question was, now, since in phase one, we showed that each vehicle can guess by itself the cause of congestion, the question becomes, if the vehicles can share their knowledge with each other, like in the vicinity, will they be able to better assess the traffic situation experience? And here again, we experimented with different data mining methods and tested belief functions that combine degrees of confidence about events. We also tested a data association technique and we uncovered association rules in the data set. And those rules were actually enabled us to extract relationship between seemingly unrelated data, and this added more knowledge to the system. So this also led to a publication in IEEE Transactions on Intelligent Transportation Systems. Now, in phase three, for example, another question that we had was, how can we predict traffic flow on a segment? Okay, the flow of traffic, number of vehicle per second, with a model able to adapt to any varying traffic situation around it. And so the final idea was a traffic flow prediction model that considers not only past flows on the segment, but also incorporates in the prediction problem the real time events that those connected and autonomous vehicles were sensing. Meaning that we were able to show that using the estimation of the cause of congestion that we were able to do earlier in phase one and phase two, and using features such as the experience of a vehicle along its trajectory, connected and autonomous vehicles can help in the prediction of traffic flow on a segment. In this work, particularly, we trained a deep neural network for short-term traffic flow prediction, and we proposed that the classifier learns to solve multiple tasks at the same time in a multitask learning setting in deep learning. So these contributions led also to a publication in IEEE Transactions on mobile computing. And so the idea is that by solving those transportation problems with vehicular networks, our focus was just on the design of the solution, trying to find a solution. However, as the designer of the solutions and the strategies, we were able we were aware of their intrinsic behavior as well as their security vulnerabilities. So some solutions they inherit existing IT vulnerabilities, and others they introduce new ones that are specific to this the system under study. So when we discovered that some solutions introduce vulnerabilities that are specific to the system, we wanted to study different systems in order to find correlations and understand the challenges to cybersecurity in different application domains. And connected and automated vehicles, they run on a critical infrastructure and are a key component in urban transportation cyber-physical system. But cyber-physical systems are shaping our future by improving the quality of our lives in so many domains. So for the past couple of years, I have been pursuing a broader research agenda, and I was addressing key research problems in critical infrastructure other than the transportation network. For example, power grids and the energy domain, and systems in smart cities, connected vehicle system in aviation, such as air traffic control. So here I present a summary of the research I conducted on cyber-physical system and in different application domain, and I will highlight the different contributions. So in the computer networks domain, I worked in collaboration with the LARIM research lab at Polytechnic, and we were working on software-defined networking and this technology that provides programmable control over the network elements and provide visibility. In the transportation domain, I worked in collaboration with Professor Bilal Farouk at Ryerson University, and we developed a cybersecurity risk assessment framework for blockchains and smart mobility. Um, in the energy, for example, production domain, I worked in collaboration with Hydro-Quebec and its research institute with Professor Andrea Lodi. In particular, it was in microgrids where there is a new generation independent, like those regional networks with both local producers and end consumers, and we worked on analyzing the resiliency of the control algorithms used in microgrids, and their resilience against malicious input. In the road traffic control domain, I worked in collaboration with the civil engineering department at Polytechnic, and we studied reinforcement learning agent based um, to attack adaptive traffic signal control. Um, Finally, in the air traffic control domain, I worked in collaboration of the Information System Security Lab, where we work on an ontology development for a security expert system here. So I'll now present my ongoing research, and this is the research that focus really on the security in the design of all those solutions. And I classified the achievements in terms of attacks and defenses, just to highlight the key difference, the key realizations, what we realized. So on the attack side, we were able to analyze an electrical network, um, particularly, as I said, the microgrid control algorithms that run on the microgrid. We were analyzing them against malicious input. And microgrid security research generally focuses on either characterizing or preventing attacks on the devices or on the communication infrastructure, but we instead investigated security concerns in microgrid control logic. And um, the controller was less performant, obviously, when it was faced with false data injection attack scenarios. And similarly, in the other two works that I state here, for example, for the adaptive traffic control system and the connected and automated vehicle, in all the works that we done and tests in different in all works that required some control algorithm, we were able to attack it in the same manner, and we came to the realization that sophisticated attacks, they understand the control logic, and this in any cyber physical system application domain. Okay, so now in terms of defenses, we worked on a cryptographic solution for ADSB, which it's an automated dependent surveillance broadcast. It's a message sent by an aircraft. It's a surveillance technology where the aircraft broadcasts its position based on its satellite navigation information. So, and also in another work, we experimented with those ontologies, which is a knowledge-based knowledge representation technique, because they had emerged as like a potential solution to solve problems in computer security. We tested them for anomaly intrusion detection systems, and after working on the defenses, we realized that good defenses are domain specific. In fact, like those existing domain agnostic defense mechanisms, they are too generic to be able to understand and detect the previously tested targeted attacks under the cyber physical systems, where only an expert, a domain expert, a knowledgeable domain expert is anticipated to protect the system via a concept called security by design. So we came to the realization that a good security posture could not rely just on products, on independent security products alone. It requires good situational awareness in terms of detection, response, and it requires research to be done on monitoring, analysis of information, coming not only from the multitude of decentralized connected components of the system, but also from the correlation of the information with other relevant data sources. So now, securing large-scale cyber-physical system is hard to do. Also, the diversity and the heterogeneity of the sources and data formats involved in the cybersecurity monitoring process is not making the job easier. So, researchers and cybersecurity companies have been proposing for several years now the use of AI, and in particular machine learning techniques. So the key idea in the use of AI in cyber physical systems is that the good performance of artificial intelligence in different application domain of cyber physical system, it lies in their ability to embody the vast amount of data and large dimensions of the functionalities. Also, they embody the uncertainty due to the unpredictable nature of the variables. And so in the transportation network, for example, machine learning techniques, they embody this unpredictable nature of traffic, uh, and the myriad of factors that affect traffic flows, like the weather condition or other driver behaviors and traffic problems and events. So this is why my methodologies to support the cybersecurity of emerging cyber technologies involved AI, particularly machine learning, deep neural networks, federated learning, and reinforcement learning. The vision is that AI in cybersecurity can be useful, but not by blindly applying machine learning and deep learning approaches. This AI technology has its own challenges. And among the challenges in AI is the question, for example, of explainability. Why did the AI do it, especially in black box approaches? Also, the question of transparency and ethics in terms of what is the AI looking at to make this decision, because we don't want like unwanted or unknown or illegitimate bias. So there's also like the adversarial AI, and I will discuss later this AI versus AI arms race in that sense. So I will now present like different little project where we leveraged AI techniques in cyber physical system security. Um, Federated learning is a machine learning technique, and it aims at training an algorithm across decentralized entities that hold their local data private. So, despite the advantages of this AI technique, there is an increased potential of cyber attacks on FL based machine learning techniques that can undermine those benefits. And one of them is this untargeted model poisoning attack on federated learning. So this attack targets the availability of the model, and I'm trying to show it in this figure, the impact of the attack. So the attacker, or more it's the so the adversarial objective of the attacker is to disrupt the training of the model being trained by the workers in the federated learning setting. And current defenses, they looked at robust aggregation techniques to protect against this type of attack, that is sending poisoned local model updates. No study looked into the behavior of the worker. And so what we did, we proposed a untargeted poison and attack detection technique in federated learning that is based on behavior attestation. And the idea is to monitor the training of individual nodes through state persistent in order to detect a malicious worker. And the intuition is that if we can monitor the history of this worker, we can assess their behavior in time, and we can remove those unreliable nodes from the aggregation process so that the FL technique, the FL model converges faster. Um, so this is another work here in AI-based cyber-physical system security. So to achieve decentralized federated learning, blockchain-based federated learning was proposed as a distributed federated learning architecture. And As you know, a blockchain is a shared ledger that maintains like a list of transaction records, um, which cannot be altered unless a consensus in the network is reached using an algorithm. So, in decentralized federated learning, the concept is that the chief is eliminated from the learning process, and now the workers they collaborate between each other to train the global model. And decentralized federated learning application, they need to account for the additional delay incurred by blockchain based federated learning deployments. So in our work, what we did is we investigated this end-to-end learning completion latency of a realistic decentralized federated learning process, um, that is that was protecting against poisoning attack. So what our technique does is that it decouples the monitoring phase for the detection from the detection phase. Uh, in defenses that aim at monitoring the behavior of the workers. So when we do this parallelization of operations, it results in minimized latency over the end-to-end communication, minimized computation, and consensus delay incurred during the federated learning and blockchain operations. So in this work, we were able to demonstrate that our blockchain-based monitoring improved network scalability, robustness, and time efficiency. Um, Now, here in this work in the transportation domain, we exposed cybersecurity threats in connected and automated the vehicles-based federated learning system. And the thing is that the road traffic network is a infrastructure-based configuration. It has an infrastructure-based configuration of a but it's a wireless mobile network on it, where the connected and automated vehicles are the communication entities, the communicating entities. So applying federated learning in a wireless mobile network setting gives rise to a new threat in the mobile environment that is very different from the traditional fixed network. And the threat is due to the intrinsic characteristic of the wireless medium, and is actually caused by the characteristic of the vehicles on the network, such as the high node mobility and that rapidly changing topology. So in this work, we explored an attack that we called a falsified information attack, which targeted the FL process again that is ongoing on the roadside unit, meaning that one fake vehicle was able to fabricate with fake identities. He was able to corrupt um, by doing a single shot attack and compromise the training of the federated learning model that was ongoing. So we identified a number of attack strategies to also disrupt this training, the training. And again, in that another work here in the transportation domain, adaptive traffic control systems, they are emerging as a promising solution for urban traffic control. What they do is that they form a network of intersection, and they continuously adapt traffic light timing to meet the real-time traffic demand. Okay, a network of smart lights, traffic lights. So however, due to the lack of security of the controllers, again, it's the control algorithm. So, due to the lack of security of this control algorithm at the intersection, the system becomes vulnerable in terms of availability and integrity. And we implemented a deep reinforcement learning based agent and trained this attacking agent, to target some critical intersections in an urban grid network using an algorithm called proximal policy optimization. So we saw that the attacker was able to learn a strategy. He was able to learn how to tune the parameters to maliciously disrupt traffic signals, either by spoofing the information or by sending illegitimate commands and control instructions to the traffic lights. So the agent was able to create his desired disruption by increasing the congestion. And so deep reinforcement learning based agent took control and degraded the performance of this adaptive traffic control system that was in place, and it degraded it in terms of delay and vehicle density in a given intersection. So finally, in this work, we know that connected and autonomous vehicles, with their evolving data gathering capabilities, they're going to play a significant role in cities, particularly when it comes to road safety and efficiency applications. And this unfortunately will also expand the space of security vulnerabilities and create larger threat vectors. What we did in this work is that we performed an implementation of a new attack carried out by the network of connected autonomous vehicles on intelligent transportation system, and we called it the coordinated cyber attack. What happened is that the vehicles with forged or fake identities, they try to alter the data that was collected by this system of collaborating intersections, and they were able to sabotage the decision made by the algorithm. Again, then for this work, we proposed a game theoretic mitigation approach to defend at the application layer to minimize the impact of the Sybil attack that was ongoing. Now, my long term research objective is to explore this AI versus AI arms race in cyber physical systems. And it will be extremely difficult within a 5 year, for example, scope, for example, to create a foundational mathematical theory of this co-evolution that can allow us to answer like fundamental questions about the convergence and equilibria of such an arms race. And although it will be the ultimate goal, instead, we'll attempt to spur research in the area by providing experimental data sets and evidence of the phenomena. And this will hopefully inspire attempts at constructing this theoretical mathematical model for examining and describing this concept. So, these are some of my short term objectives. The first is to provide AI based methods to improve cybersecurity analytics by enhancing monitoring and developing AI based tools and methods to modernize, automate some detection, correlation, and analysis functions. Another objective is to model and experiment with those sophisticated attacks in order to understand them and be able to design new class of domain-specific defenses against those attacks. And the third objective is to explore this the resilience of cybersecurity solution and attempt to model and understand this potential AI against AI arms race in cybersecurity. Now, this is a visualization of the arms race that we will be witnessing, this AI against AI. I laid down a lot of interesting concepts on the figure. In the middle, the concept of co-evolution. When the operating parameters like the control discipline, the network config, or the environmental conditions change, so when the factors change, we talk about a co-evolution scenario, and where we can evaluate, in this case, the robustness, how robust our solutions are against non-adversarial changes in the environment. And in the case where those operating parameters do not change, we will be evaluating something called co-opt. We would call it a co-optimization scenario, and in this case, we will be evaluating the resilience of the attacks and defenses against maybe changes of strategy of the adversary. So on one side we have the attacker, and on the other we have the defender, and each has a set of defined action he can take, and each machine learning model is learning a strategy based on what it is sensing from the environment. So we will explore and attempt to model and understand this potential arms race in cybersecurity. And it's on physical infrastructure that we will be able to appreciate it the most, because the physical impact on a critical infrastructure can be observed in terms of concrete metrics and measurement, like the number of vehicle congestion. Those metrics are important to assess the impact of this duality between AI versus AI. Finally, I have been addressing key research problems in critical infrastructures, and the challenges of assessing cybersecurity is that in complex systems, um, systems domain are so interdependent and interconnected, and sometimes known and unknown threats may impair the integrity of the system as a whole. And and since my research interests are in applied machine learning and my methodologies involve artificial intelligence, my long term research goal is to study this AI based resilience in cyber physical systems. And in terms of impacts, we'll be able to efficiently detect sophisticated cyber attack. We wish to be able to efficiently detect sophisticated cyber attacks, and also there will be benefits in terms of advancement of scientific knowledge beyond cybersecurity. We will be able to explore the outcome of the arms race and hopefully have a better understanding of AI security. Thank you very much for your attention.
Thanks a lot, Ranwa. That was a great talk. And unfortunately, I don't think so. We'll have too much time for questions, because we
Mm,
lost some time at the beginning of this whole presentation because of technical difficulties. But we have, like, perhaps I'll ask a couple of questions. So there is a question from Shalab. Like, let me share that on stage.
mhm.
So basically, his question is that how can industry and academia work closely together, and how can industry help academia like tackle some of the problems that you're looking to solve?
Yeah, for sure. So the problem is that obtaining sufficiently large and representative security data sets has always been a major hurdle for security researchers. So we have a requirement in science that other researchers they must reproduce our results. So it's important that this scientific requirement of reproducibility of results is important. So how we can come together is by this collaboration and giving us access to more data set, because new attacks when we have new attacks we can't our models are trained with past data sets, and so if we don't update our data sets with the current traffic, current information, then we won't be able to detect those new attacks that are occurring. So every model that we train depends on the data set it's trained on. So collaboration like this is very important in for academia.
And in the absence of these data sets, like what's the approach? Like, do you use like synthetic data sets? Do you basically like emulate like environments which are close to real environments? Like what approach do you go with for like for training your machine learning models and for validating your hypothesis?
Yes. So yes, in intelligent transportation system, the quality of this data set is like one of the most important factors. And we do use like fortunately for like historical data and models, for example, in origin and destination matrices in road traffic networks. So with these models as input, we are able to generate data set from this, and we call them synthetic data sets. But another thing that we can do is that we can use reinforcement learning, like change technology reinforcement learning approaches. What's interesting with this AI technique is that you don't need a data set for training. It just needs a realistic environment, and it operates on this environment, and it learns from its collected experience on the environment. So it creates its data and experience. So this is how we can work with the scarcity of data set, or with the making things even more accurate.
For sure. And yeah, I think like with this we'll have to end the session. But this was a great talk, Ranva, and thanks a lot for the talk and for your time, and thanks to the audience as well for listening to these sessions. All right, thanks all. I'll end the session.